Like Dr. Prannaru said, I'm co-supervised with computer science and health. And so my projects are kind of at the intersection of the two and trying to see how machine learning can be used to help healthcare in general. And the project that I'm going to present is grading appendicitis with machine learning. But before I get too much into the project itself, I'll give a bit of a background as to what machine learning even is. So machine learning is basically a conglomeration of different types of algorithms that learn patterns in the data and then utilize these learned patterns to make predictions. So for instance, if I wanted my machine to learn how to recognize a dog, I would feed it or use data for images of dogs and images of things that are not dogs. And it'll start learning patterns. So it might learn that dogs have fur or dogs have big ears and two eyes. And it might also learn that things that are not dogs, maybe they have scales, maybe they're blue, maybe they have no eyes. So whatever patterns it learns, it can then utilize these patterns to make predictions. So the prediction in this case would be if I give it a new image, it might be able to predict if this is a dog or if it's not a dog. Then there's different types of machine learning. So the example that I just gave is an example of supervised machine learning where you have data with a label that you're trying to predict, and then it learns patterns on how to map this data to what you're trying to predict. And then if you just give it the data, it can predict the label. There's unsupervised, which has the data but doesn't have the label. And there's reinforcement learning, which is a whole other thing that I'm not really going to get into. For this project, I'm only using supervised learning. Then within this type of machine learning, there's different types of tasks. And two of those main tasks are regression tasks. So this means predicting continuous values. And there's also classification task, which is predicting discrete values. So another example of this would be if we want to predict the price for a house. Let's say you have data, which is how old the house is, how many bedrooms it has, what's the square footage. So these are all variables that are x1 through xn. And you're trying to predict the price, which is a continuous value, which we're going to call y, so our dependent variable. The pattern that the machine can potentially learn are these A1 through AN, which are the weights or the coefficients, which basically determine, how much each variable contributes to predicting y. It's not always just an equation that's this simple, but the general idea is the machine is learning an equation that maps the variables onto y. A classification task using the same example could be using the same data, can we predict what neighborhood this house is in? So that would be classification. Another component to this project is just the general problem sets that health data sets that come with health data sets. So they're usually quite small, and small data sets are usually an issue because they don't really help with training that well. The results may be inaccurate. There's also a lot of missing values. And just intuitively, this makes sense because not every patient is asked to take the exact same test or the same amount of CT scans. They don't have the same history always. So it's basically expected that every patient record is a little bit different from each other. Some patients have a recorded value and others do not. There's also a problem of imbalance. So that's when one group is shown a lot in the data set and one group, the minority group, is not shown very much. And this can create a problem of bias in the resulting model, because if there's bias in the data set, which the model learns off of, the model will then have bias. So there's been issues in the past, for instance, where they have a model trained on a predominantly male data set. And so this model is great at predicting things for the male population, but is horrible for females. And so we want a fair model, and that comes with a balanced data set. Another issue is that it's usually hard to obtain, and that's just because of privacy regulations. But solutions do exist to these problems. So one of them is that you can fill in these missing values through a process called imputation by predicting them with machine learning, actually. So that's one thing that I did in this project that I'm going to talk about in a bit. And there are also methods that exist to deal with unbalanced data, which I will also talk about. So the project's research question now is, can we use pre-operative health data to predict the grade of appendicitis? And by grade of appendicitis, I mean simple or complex appendicitis. So can we predict that grade with greater accuracy to other preoperative diagnostic tools? And so the baseline that we use is the ultrasound diagnosis, which for our data set has only a 66% accuracy. And the whole idea behind this project is to actually help with clinician decision-making pre-surgery, to help them understand how urgent it might be for a patient to get medical care or surgery, and just the grade, or if they need to get surgery at all, just to inform the clinician. So our data set is a pediatric appendicitis data set with approximately 2,000 patient records. We have both pre and post-operative data, which includes demographics like age and sex, history. So does this patient have fever, anorexia, nausea, laboratory investigations, white blood cell count, and urine analysis, for instance, operative data, so the name of the procedure, post-operative diagnosis, ultrasound reports, operative reports, and pathology reports. And since, just to remind you, our research question is, can we use pre-operative health data? That means for our X values, the data that we're using to predict our grade should only be pre-operative values. That means that we're getting rid of operative data, operative report, and pathology report, which usually come post-surgery, and only focusing on the ones that are pre-surgery. So we're doing this with the exception of peritonitis, perforation, and abscess, because these three things are actually going to be our Y values, what we're trying to predict. Because once we have predicted each one individually, we can then use them to calculate the final grade of appendicitis, which is what we're interested in. So machine learning is actually used in two different ways in this project. The first way is to fill in these missing values, again, through a process called imputation. And the other one is to predict individually abscess, peritonitis, and perforation, which will then help us determine the grade of appendicitis. So a little flow chart is at the bottom here. You have the original data set, which the white blocks are the missing values. You impute the original data set, so fill in these missing values. And then you balance it using one of the balancing methods that I alluded to earlier. And using this balanced data set, you create machine learning models that individually predict abscess, peritonitis, and perforation, which are used for the appendicitis grade. So hopefully that makes sense, up to date. For the machine learning algorithms that I've tried, to fill in the missing values, 6 different algorithms were tried in 2 different ways each. I'm not really going to go into the 2 different ways just to keep it more on the simple side. But what you need to know out of this is that there's 12 different data sets generated. If you use a different machine learning model, it'll produce or potentially predict things in different ways. And so produce different results and produce different filled in data sets. Then for balancing the data set, there are 3 different methods that we've tried that I'll talk about in a bit. And then you need to create a model to predict abscess, peritonitis, and perforation. And to do that, I tried 5 different classification models. So basically the combination of all these different things that you can select from led to 540 different models or combinations of these things being tried. So for instance, one combination would be you use one type of algorithm to fill in these missing values. Then you use one possible method to balance the data. You predict abscess and use this classification model to predict abscess. So that's one way through the tree of options. So how did we actually fill in these missing values? Remember, there's the X values, which are variables that we're using to predict the Y value. Over here in our original data set, you can see that there are some features or values, or sorry, variables that have no missingness in them whatsoever. So these are our X values. Then you have features that do have missingness, and we're going to take a turn going through each of these variables that have missingness, and they're each going to take a turn being our Y value. So you use these X values to predict the Y value. There are some rows, so some patient records that contain this value and some that do not. You split them, so you have a data set of a fully complete data set that includes known Y values, and then you have a data set that has all the patient records with that Y value missing. Using the complete data set, you train your machine learning model, and then you apply your trained machine learning model onto the rows with missingness to impute them or predict them. You then just concatenate the known Y values and the predicted Y values, and that is your fully complete filled in feature or variable. You do that for each of the variables that have missingness to ultimately produce this fully imputed data set. And remember, there are 12 different ways you can impute this, meaning that we have 12 different imputed data sets at the end. The second way that we use machine learning is once we've imputed our data set, once we balance it. So one method is upsampling. So you have the minority class and you're just copying certain rows for the minority class until the minority class is equal to the majority class in number. Another way is similar to that, as in you are upsampling the minority class, but you're doing that by not copying, but you're creating synthetic data to get the same number of patient records in each class. And then the other one is just the baseline, so we don't do anything to it. And then you have 5 different machine learning models that are listed above here: KNN, decision tree, SVM, random forest, and logistic regression. You don't need to know what they are, just know that they are different machine learning models, and you test them on each of the data sets. So overall, this is what's happening. You have your original data set, it has missingness. You fill in these missing values, you get 12 imputed data sets. You make a data set specific for each of the things that you're trying to predict. So one data set with all the filled in missing values plus abscess. Same thing with perforation, same thing with peritonitis, because that's what you're interested in predicting. You balance these data sets in 3 different ways, and then you try these 5 different Y values to predict abscess, perforation, and peritonitis, which are then used again to calculate the grade, the final grade. So hopefully that generally makes sense. As the project stands right now, we're done filling in the missing values and done balancing the data sets, and I'm almost halfway through predicting the Y values. We just take the end result with the highest accuracy as our final model, because we know that, let's say if we fill in missing values in this way and we balance the data set in this way and we use this machine learning model to predict our Y values, we get the best accuracy, and we hope that it's better than what we have right now to predict the grade of appendicitis pre-surgery. So that it means that we actually contributed to something or improved something. And that is all. Are there any questions?